again. Um, all right, so uh, just some common rules and regulations. Yeah, it has started recording. Some common rules. Please feel free to unmute yourself and speak up. So I'm not looking at the chat box. I'm looking at my screen. So whatever you want to say, just unmute yourself and speak out. Please don't just listen. That is one instruction. Speak up wherever you required, whatever you don't feel you have not understood properly. Um, just speak up. There's no point in just keeping silent. And most important instruction is you should have a pen, a piece of paper, and a scientific calculator ready, because we are only going to do calculations in this whole course. So the name of the course is Material Energy Balance Calculations. So we are going to do calculations all the time. Uh, all right. So let's get started. Let me take you through some of the basic concepts that we are going to use, not just in this course, but in other chemical engineering courses and other courses that are going to come in the next 3 years or so. Uh, why don't we start with somebody telling me about manufacturing of any particular product that they like or that they want to discuss. So somebody can speak up on how do you think some particular product is manufactured. So it might be a pen, it might be rubber, it might be ice cream, it might be cake, whatever product is of interest to you. Tell me how it is manufactured. Then we will talk about that.
So,
From raw materials.
Yes. So who wants to say? Praveen Kumar. Yeah, go ahead, Praveen Kumar.
Sir, from raw materials and different processes, there are.
No, you tell me first name of the product that you are manufacturing or that you want to discuss about it today. Then you tell me what are the raw materials and how is that product made.
I think uh, glass, maybe glass.
Glass. All right. So you want to make glass. Okay. So glass. So how do you think glass is made?
Silicon oxide, SiO2.
Okay. So silicon dioxide, SiO2, and then what?
And many other, the the metals are also there,
Like what?
the transition metals
Which
like
ones?
iron for different colors and many other
so,
things.
transition metals like molybdenum, if you want blue color
Chromium is
glass.
also there. The
Okay.
chromium oxide.
All of them are oxides. Chromium oxide is in what form? Cr2O3, 3 plus valency. Molybdenum oxide, plus 2 valency, plus 4 valency.
Plus 2, I guess,
Okay,
Plus
molybdenum.
two.
okay,
Plus
okay,
two.
okay. Chromium oxide. Okay, what else? Okay, you're forgetting one of the basic ingredients. So these are all there to put colors. Glass is what?
Silicon dioxide.
And what is the composition, or what are the
Al2O3, I think.
Al2O3?
Sand.
I
Aluminum.
think no.
Glass is dash dash silicate.
Aluminum silicates,
Not aluminum silicate. Dash is a
borosilicate.
borosilicate, right? So along with that, you need a boron source, right? I'm just writing B. You can have any other any compound of boron. It can be boric acid. It can be
Tribor,
boron. Besides boron, what else is a? It's a silicate of what?
Magnesium oxide.
Magnesium. Okay, maybe
The sodium silicate.
sodium, right? Sodium, right? So it's a sodium silicate. So you need sodium first. You need silicon. So silicon, we take it in the form of sand, silicon dioxide. All right. So what do? You take all these materials and then do what? What do you do with all these materials?
So heating.
So we put them in a crucible, and then the crucible is
Right.
put
So
in a furnace where all these are led to melt and
so you
or it is a semi-solid state where it's not completely melted.
right. So can we
We
say
first mix them and make a coarse mixture of a
right? So can we say that we will all mix them?
particular particle size first.
Okay. So we have to grind them first. Is that what you're saying? Grind them to a fine powder. Is that what you're saying? I don't know who's saying, but because I'm looking at my screen. So you want to grind them first, then you want to mix them, then you want to heat them. What do you want to do? Heat,
Then mold, I think.
melt them, yes, and then what?
Yes, sir.
Mold.
Yes, sir.
Okay, and then what?
Mold them, mold.
Yes, sir.
So we will have a
Yeah.
molten mass. Molten mass. We will have molten silicate, molten
So we
sodium
transfer them
silicate.
in a crucible and then we heat them to a particular temperature, and then we mold them according to what.
Right. So,
Yes.
do you think some of these? So, if you say sodium silicate, let's just forget that there are other things right now. Let's say this molten mass is sodium silicate. It is not just enough to melt them. You have to wait for them to react together, isn't it? To make sodium silicate. Do you think water will be formed? Because this edge, suppose even if you don't consider all of these things, even if you don't consider any of these metals and colors, what is going to happen to this hydrogen atom that is there from sodium hydroxide? That has to go away as water. Do you think so?
Vapor,
Because
sir.
water does not appear in the glass, water does not appear here, isn't it? Only when they react, only when these two react together, then only this sodium silicate will be formed, then only this water will go away. Do you agree with that? Yes, no, somebody say something.
Yes, sir.
Yes,
Right.
sir.
Yes,
Yes,
sir.
sir.
Okay, then what do we do with this molten glass now? Now that we have a molten glass, what do we do with this molten glass?
Mold them, mold.
Cooling.
So you put them. Okay, so you put them in a mold if you like, and then you cool them, and then you take it out, and then now you have a glass. Let's say glass decorative piece. You want to put that decorative piece, so you will have that mold which has that shape of that decorative piece. So the glass will solidify, so to say, and it will take the shape of that mold. And then once you take out that mold, then we will have our glass piece. Okay. Any other product that we want?
Paper.
Paper. All right. Paper. Right. Correct. Correct. Paper. Yes. Yes. So paper. How do you make paper?
Anything.
So
Green
we
leaves.
extract
Grass.
wood pulp. We extract wood pulp
Pulp.
and then we bleach it and make
Well,
fibers of it.
let's go slowly. So when you want to make paper, what is it that you are doing? You need some wood source. So some tree is required.
Yes, sir.
Okay. So what do you do with that tree now?
So we
Cut them.
cut them and then we make or we shred them basically into their fibers.
Okay. Cut, shred. Okay. What else?
Put NaOH and then
NaOH.
No,
NaOH
sir,
does
we
what?
bleach them.
Mix them with what?
I mean,
So okay, we will mix that cut shred and mix them. Okay, what do we do next?
Sir, we bleach them.
Bleach using what?
Uh, HClO.
HClO. What is HClO? Wo- wo- Perhaps you mean sodium hypochlorite?
Yes, sir.
We don't use HOCl, we use sodium hypochlorite. Another thing that is okay, so you bleach and then do what?
Uh,
and then flatten them
But
to
after
get.
you bleach them, don't you want to separate the fibers from the bleached solution? Otherwise,
Yes,
the
sir.
color and all those matter that you have bleached out, that will remain in your paper. You will not have a white paper. You will have a black or a brownish paper, right? Or
Yes,
yellowish
sir.
paper. So it is not just enough to bleach. You need to filter and separate out the solution, and then you will have your fibers, isn't it? Bleached fibers. Now what do you do?
compress them together.
Okay, so you want to compress them together. Now what?
And let them dry.
Trying.
Dry, right? So how do you compress?
Applying
Many
pressure
options
on
are
both
there.
sides.
Apply pressure. How do you apply pressure?
Placing a weight
Placing a
on the
weight.
weight
Okay,
on them.
placing a weight. Now papers are made in kilometers per
Hydraulic hydraulic
hydraulic
pump.
press, hydraulic pump, hydraulic press. Okay, uh, so we will need electricity to operate that. In fact, we will need electricity to operate the filter. We will need electricity to cut this machine, cut this wood into fibers. Don't you think so?
Yes, sir.
So I'm going to write it up with another color. Electricity. Perhaps electricity is required here. Perhaps electricity is definitely required here. Cutting the fibers. Right. Same way electricity would be required for all these various operations. Okay. Now dry. How do you dry?
By heating it, but the temperature matters over here. We cannot go on heating it.
So heating to what temperature?
So using a iron type thing.
Iron means the home wala iron, which we iron the clothes with. Wo wala iron.
Yes, sir. Yes, sir.
Well, all right. So you have to have heated. Uh, what you need to do is you need to have heated rollers. So papers are not made by one A4 sheet at a time. They are made in a continuous process. Anybody seen any time paper mills? It's a continuous process. You just make the paper as a one big roll, and then you cut it to pieces and whatever you want to do with it. So heated rolls up to a certain temperature. So you need a heat supply. So that heated rolls, you many times heat using steam. Right? That's what you do when you iron your clothes at home. That's what is generated. Either you do steam heating or you whatever clothes are slight moisture is there, steam is generated, and that's how the um, wrinkles are removed. Okay, any other product we would like to talk about?
So rubber.
Any other chemical that we would like to talk about? It doesn't matter. Okay,
Ammonia.
these are chemicals.
Ammonia.
Ammonia. All right, let's take ammonia. Okay. Uh, okay, how do you think ammonia is made?
Haber's process.
N2 plus H2.
Haber's
N2
process.
and H2. Where do you get N2 from?
Atmosphere.
Fractional distillation of
Fractional
air.
distillation of air.
Or a Bapre. So you take air, you do fractional distillation.
So that will require energy to cool down air at that temperature.
Right. So you will require energy. Fine. So you do fractional distillation of air. So what do you get when you do fractional distillation of air? You get nitrogen. What else do you get?
Oxygen,
Oxygen. What else do you get?
other gases, but
Which other gases? Which is the other major gas that you get?
Carbon dioxide.
carbon dioxide, but that will solidify.
So carbon dioxide you don't get by fractional distillation. Which other gas? Carbon dioxide has to be separated first.
Argon,
Argon. Right. Okay. So this nitrogen you want to use here. Is it?
yes, sir.
Okay. What do you do with this oxygen and argon?
We give it back,
Store it or
or
sell it to other
yeah.
We can sell it.
industries.
Oxygen we sell to COVID patients. Isn't
Yes,
it?
sir.
Well, I'm just giving some example which is live just now, but oxygen there are so many uses. Like you can send it to a steel manufacturing company also. They will have this air separation. That's how all these steel people were able to give oxygen to all these patients. Argon, what do you do?
Bulk manufacturing industry,
Bulk.
sir.
Bulb. In
So
bulbs.
we can store it and send it to laboratories where they need inert atmospheres to work.
All right, so argon has some very special uses. Let's not get into that just now, but some of these nuclear plants, they use argon as an inert atmosphere uh, for that nuclear reactor. So let's not worry about that just now. Okay, so now that we have got nitrogen, how do you get hydrogen?
The electrolysis of aqueous NOH.
Bapre.
So by fracking of uh,
Alkanes.
of fracking of alkanes.
uh, did you say fracking? Fracking? What did you say?
Cracking.
Cracking.
Fracking or cracking?
Cracking.
Cracking.
Oh, okay. Cracking. Okay. So cracking of alkane. Which alkane?
Long chain alkanes.
Which
10
one?
or
Tell me a name.
octane, nonane.
Octane. Okay, octane you crack. Then what do you do? What happens when you crack octane? What do you
So
get?
we get a smaller alkane and a alkene plus hydrogen.
So you get alkanes, smaller alkanes. So let's call them as C2, C3, C4, maybe C2 double bond, C3 double bond, C4 double bond, maybe C1 also, methane also. Okay. And you get hydrogen also. Okay, now how do you separate this hydrogen from this C1, C2, C3, C4?
H2 is gas and rest are, I think,
H2?
also
How do you separate this hydrogen?
So by cooling them,
Okay, cool it. Then what happens?
so the alkanes would liquefy at a higher temperature than hydrogen. So hydrogen would still remain a gas under
Alkanes.
pressure.
Okay, alkanes will liquefy. Methane doesn't liquefy so nicely. But okay, assume that methane also liquefies, then you get hydrogen. That's what you are using here. Is that what you're saying?
Yes, sir.
All right. Now, what do you do with this nitrogen and hydrogen?
Haber's
Haber's process.
Haber's process. So, what does Haber's process involve?
Fe and MO.
Molybdenum.
That's a catalyst. What is
Sir,
the
first
temperature?
compress
Sir, we
gas.
700.
See, one
So
second.
673 Kelvin.
Yeah. One second. So this nitrogen that we have got, that is coming from fractional distillation. It is coming at low temperatures, isn't it? So let's say this nitrogen is 77 Kelvin. I want all these alkanes to liquefy. That means this temperature also will be lower. Maybe let's say 100 Kelvin. So we have nitrogen and hydrogen at low temperatures. 77 Kelvin is nitrogen, 100 Kelvin suppose is hydrogen. Now I have to have a high temperature process. Do I not need to heat first?
yes, sir.
Yes, sir.
Yes,
Yes, sir.
and pressure also.
And pressure also, right? So I need to compress. Okay, so I will compress. So now I will have nitrogen and hydrogen at high temperature and pressure. Now I will send it to catalyst. I will allow them to react. Then will all the nitrogen and hydrogen react?
No.
sir.
No, sir.
No.
The remaining will also send back to the
So
process.
I will have nitrogen, hydrogen and ammonia that is formed. Now how do I separate the nitrogen and hydrogen and ammonia?
Cooling,
Ammonia will be
liquefy.
liquid.
So I will cool. We will liquefy. Then we will take out the ammonia. What happens to nitrogen and hydrogen?
They are sent back
Huh.
to the
To
process.
where?
To the
To
first
the
process.
reactor.
To the reactor.
To the reactor. Can they be sent back to the reactor just like that?
No, first they need to be heated and compressed again.
Alright, so they may have to be heated because you have cooled them, isn't it? You have cooled them to liquefy the ammonia. So here also I will need to heat. Here also I will need to compress. Isn't it? Now tell me, which steps will you require energy?
Heat,
So cooling, heating.
cooling, heating,
So
cracking.
we talked about
Excuse me,
this.
sir.
Yes.
Sir, in the last step where we sent N2 and H2 back, sir, we don't require heating because the reaction is exothermic, na?
But for separation, you are cooling them, right?
See, for separating this nitrogen, hydrogen, ammonia mixture that has come out here, that is at high temperature and pressure.
Hmm.
Now, unless you cool this whole mass, then only ammonia will liquefy and separate out, right?
Yes, sir.
I can't just cool one component from this gas mixture. I will have to cool the whole gas mixture.
Hmm.
So maybe this gas mixture is cooled to, let's say, maybe 100 degrees centigrade. So this ammonia liquefies, nitrogen, hydrogen liquefy, or maybe 50 degrees centigrade, whatever is the critical temperature of ammonia. Now, so these nitrogen, hydrogen are at low temperature. Don't I have to heat them to get to the reaction temperature? Suppose the reaction temperature I want is 500 degrees centigrade. I will heat up this incoming nitrogen, hydrogen to 500 degrees centigrade. If I mix with a cold nitrogen and hydrogen, my reaction temperature will go down, isn't it? I will need to ensure
Yes,
that
sir.
they are also at high temperature. Is that okay?
Yes, sir. Thank you, sir.
Yeah. So now tell me, which processes require energy?
Heating.
Cracking.
Fractional distillation we talked, it requires energy. Cracking, do you think energy is required?
Yes, sir. We need to
Yes,
heat
sir.
it.
All right,
Heat them.
heat. So what temperature do you think cracking happens?
700 Kelvin.
Yeah, 700 centigrade more or less. Yeah, or 500 to 700 centigrade. Okay, 700 Kelvin is okay. Cooling?
Yes, sir. That will
Yes.
also require energy.
No, cooling doesn't require energy. Cooling means I will have to take out energy, isn't it?
Uh,
So, sir, we
So,
will have
but
to
even to
apply some
take out,
cooling system to it. So, the cooling system would require energy.
Right. So that cooling system will require energy to operate, just like the refrigerator at your home. Your refrigerator cools, but it requires electricity to run. Right. So you are right. But yes, overall, we need to take out energy. We'll talk about refrigeration. We will talk about how cooling is produced. All those things we will talk about as we go along. Okay. So heat is required again when you heat is required and energy is required here. Compressor. Do you think energy is required in compression?
Yes, sir.
Yes, sir.
yes, sir.
Right. Reaction,
Obviously.
exothermic
Uh,
reaction, endothermic
so,
reaction.
how would compression require energy?
Uh,
Because this is a gas compression, so it is just the amount of gas you would fill would create the compression gas.
isn't it? But how do you fill that gas? Suppose I have to fill a cylinder of oxygen. Let's say oxygen cylinder is required for a COVID patient. Now oxygen is abundantly available in air. Can I fill a cylinder to high pressure by using atmospheric oxygen? I will need energy to make that cylinder full of oxygen, right? I will need to keep on pumping oxygen into that cylinder so that it becomes at a higher pressure, isn't it?
Yeah, understood, sir.
Right. So I will require energy for compression. Reaction, do you think energy is required?
So energy would be given out.
Energy would be given out. Why is that?
Exothermic.
Exothermic.
Exothermic reaction.
Exothermic reaction, right? So I need to take out heat. Otherwise, temperature will keep on increasing because it's an exothermic reaction. So if I have to maintain temperature of 500 degrees centigrade, I will have to keep on taking out heat. Okay. Now cooling.
Sir,
Again, I will have to take out heat.
sir,
Yes. Yes.
sir, that heat we can use for heating the N2 and H2 instead of energy.
Dharmik, your voice is very feeble. I am barely able to hear you. You are
We
saying
can
something.
use the heat we have removed to heat N2 and H2 mixture.
Right, right. So what Dharmik is saying is that whatever heat we take out here, we can use that heat for heating this nitrogen and hydrogen. Okay, so that is very nice. Okay, so now what do you do? Cooling, again I will have to take out heat. This heat I will have to supply, and Dharmik will say that use that heat that you have used to cool, that same heat can be used for heating. Compression again will require some kind of energy. All right. Now, looking at all these three, by the way, just for your information, this is not how ammonia is made. Only this part of ammonia that you have told me is correct. This part is totally not correct. We will see why it is not correct as we go along. Okay? So just bear in mind that we will talk about how ammonia is made little later. But yeah, I mean, this is okay just now for the purpose of our discussion today. It is okay. Now, look at all these three. Can we make some generalizations? Can we make some generalizations? Can we have some general, uh, let's say, can we draw some conclusions from all of these, or can we look at some common features that are there in all these three processes?
So we take raw materials, supply energy, and get products, and sometimes byproducts also.
Very nice. So our process in general, I can represent it like this. There is a process We need some raw materials. We need energy. Or maybe I'll put another color. Okay. Then we will get out our product. There could be byproducts. There could be waste as well. Is that what you're saying?
Yes, sir.
Right. Just couple of things I would like to add. We might have catalyst, isn't it? We may have catalyst that is required. Maybe let's say for Haber process, catalyst is required. We may need some water. Say for example, in making paper, you need lots and lots of water to make it into a pulp so that you can bleach it. All these wood fibers that you have shredded, you need to add water so that it becomes a pulp. Then you add your hypochlorite, then you do bleaching, then you filter out. So the water, whatever water you have put in, goes as a waste solution. Right? So whatever water you have put in goes as a liquid waste, liquid effluent. Okay. So that is one kind of generalization, that this overall process we are writing, there are so many inputs to this system, there are so many outputs from the system. So if you are making, let's say, nitrogen by fractional distillation, your byproducts are oxygen, argon. Your waste is the carbon dioxide that is there in the air that you have to take out first before it goes to fractional distillation. And your product could be, it could be
N2.
ammonia, it could be N2, it could be whatever, pulp, glass, whatever is your product. All right. So one of the things that we as chemical engineers do is try to look at each and every process, or look at any process from the point of view of what are the inputs, what are the outputs, right? So all these are inputs, and what is the process that is going on. So the process could be making glass, process could be making ammonia, process could be fractional distillation, process could be compression. Each of these rectangles that I have drawn, there are several processes in that. So if you're trying to make glass, grinding itself is one process. Then mixing is another process. Heating is another process. Melting is another process. Reacting is another process. Right? For wood, cutting is another process. Mixing is another process. Isn't it? If you're making ammonia, fractional distillation is one process. Cracking is another process. Heating is another process. Compressing is another process. Reacting is another process. Cooling to liquefy ammonia is another process. Again, heating the remaining gases is another process. Compressing is another process. Energy supplying is for that compression, right? So that process, this process that we are writing in this rectangle, this could be a part of this process, or it could be a whole process. So the whole process can be like this. You can think about this as a whole process, or you can say, heating is my process, or heating and compression is my process, reaction and cooling is my process, or fractional distillation is my process, or cracking is my process. So cracking process itself will involve so many steps in that, isn't it? So we try to look at each of these individual elements of the process. We try to break them down into small units, and all these small units, we try to write them in a generalized form. What are the inputs that are coming in, what is the process that is going on, and what is the output that is going on, isn't it? Coming out of the process. Output is what is coming out of the process. Input is what we are supplying to the process. Now, so the way that we have depicted these processes, when you studied about making glass, when you studied about making paper, when you studied about making ammonia, didn't you read up pages and pages and pages? Ammonia process, where did you read? Where did you study? 12th standard, 11th standard, 10th standard, which standard?
12.
12th standard. So in 12th standard, how many pages or how many paragraphs did you read about ammonia process?
2 to 3 pages maximum.
2
Yes.
to 3 pages. Do you think that 2 to 3 pages of information is all depicted here? You tell me which part of that 2 to 3 pages of description is not depicted in this diagram.
So like the pressure conditions, the catalyst used, and all those things.
The catalyst, all right. So we can write the catalyst. We can write catalyst here, ion catalyst. In this process, I can write a brief contents, right? This process involves 400 degrees centigrade, 500 bar pressure. It requires ion catalyst. Would you like to read 2-3 pages, or do you think this diagram conveys practically all the information? Maybe some of the information may not be there, but yes, does it convey practically all the information?
Yes,
Yes,
sir.
sir.
Yes, almost everything.
Yes, sir.
Right. So henceforth, we are not going to read and write pages and pages and pages. We are going to depict processes by these kinds of diagrams. These diagrams we are going to call as block diagrams. And it is for a process, so we call this as a process block diagram. So what does a process block diagram involve? It involves block like this. For example, bleaching is a block, filter is a block, compression is a block, drying is a block, cutting is a block, or cutting, grinding is a block, mixing is a block, fractional distillation is a block, cracking is a block, heating is a block, compression is a block. Whatever we draw in this square box, that is the process that is going on in that block. We might write conditions along with the process. Operating conditions we might write. And then we draw arrows. So these arrows now tell you what is coming input into the process, the arrows that are going out of that block tell you what is going out of that block. Right? Seems silly that we are talking about so much about block and arrows, but as we go along, all these things would be clearer to you. We are going to depict processes using this process block diagram. So process block diagram is going to convey all the meaning of all the description or all the necessary things that are there happening in the process. It is going to be depicted by these squares, which are blocks, which are processes, and whatever comes into that process is going to be shown by streams. So these are streams. Another color I should have. So these are all streams. These are input streams, and these are output streams. So these streams we are going to draw by arrows and by these process, whatever is coming in, whatever is going out. So the outgoing stream is your product, outgoing stream is your byproduct, outgoing stream is your waste, outgoing stream is your liquid effluent, outgoing stream is carbon dioxide, outgoing stream is maybe some energy that is taken out from an exothermic reaction. Incoming stream can be energy, it can be catalyst, it can be solvent, it can be water, it can be raw materials, right? So now if you think what somebody was telling me, I forgot who was telling me, Dharmik. What Dharmik was telling me that we will use this heat that we have used in a heat that we have removed in cooling, or heat that we have removed in the reactor for doing reaction, exothermic reaction. That heat we will use as a source of heat for heating the nitrogen from 77 Kelvin to high temperature. So if you think about this energy, let's say you're talking about a reactor, energy is an outgoing stream. That energy can be used as an input to another block in the process. Okay, can we go little forward? Any doubts so far? Anything we need to discuss so far? Anything you would like to discuss? Anything you would like to point out? Anything you would like to clarification on? Can we go forward?
Yes, sir.
It is not necessary that CR only has to speak. Other people
Yes, sir.
should speak.
Yes, sir.
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
Okay, now let's write some things. Okay, let's classify some things that we have seen so far into different categories. Okay, I will put one category here. I will put that category as reactions and reactors. That I will put as one category. Okay, I'll just explain. So Haber process, so there is a reaction that is involved here. Okay, there is a reaction that is involved in cracking. Okay, there is a reaction that is involved in making these sodium silicate. Okay, I will make another category of let's say I will make another category, and then you tell me different things that we have seen so far in that category. Right now I will call them as some physical processes. Do you understand what I mean by physical process? There is no
Yes, sir.
reaction involved.
Changing phase,
Compression.
Right.
Heating.
Heating.
Excellent.
transferring.
Well, let's further break this down into some other categories. By physical process, can I say grinding is a physical process?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes,
Can
sir.
Yes, sir.
can we say mixing is a physical process?
Sure.
Yes, sir.
Yes, sir.
Can we say fractional distillation is a process,
Yes, sir.
physical process?
Yes.
What else can we say? Can we say drying is a physical process?
Yes, sir.
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
Okay.
Cutting.
Drying is a
Cooling.
physical process. Cutting is
Liquefying.
yes. Now I have not written, although you have been saying heating, cooling, I have not been writing all of that. Let me write that in another category: heating, cooling, liquefaction. Okay. Reason I'm writing that in a separate thing, separate box, is because I require heat for cracking process. I require heat for heating something from 77 Kelvin to, let's say, 400 degrees centigrade. So rather than writing heating or cooling as a separate, or liquefaction as a separate process, let me write it as transferring heat to a
So
process.
we can write energy transfer as a process rather than.
Okay. Let me, I will further classify transferring heat to a process, or taking out heat from a process. Now, some of these physical processes that we talked about, they also involve transfer of heat. For example, drying involves transfer of heat. Distillation involves transfer of heat, right? But some of them don't involve any transfer of heat. For example, mixing. It is, maybe I'm just mixing some powders of silica, sand, whatever, boron, boric acid, whatever other components I'm mixing. It is just a mixing process. I don't require heat for that process. I might require electrical energy for doing that mixing. Let's say we are mixing something at home, we might be using a mixer, so we will require electricity for that. But I want to bifurcate into transferring heat and using electricity. I'm bifurcating these two things just now. Of course, electricity is one of the ways in which we use heat, but it's not the only way we use heat. I can use electricity for heating water. Okay? But I want to distinguish right now between transferring heat, as in from a high temperature source I'm heating something, and using electricity for doing some operation. Yeah, so that's why I have put it in a separate category. I want to make another section. I want to make another section of transferring fluids from one equipment to another. Don't you think that is required? Don't you think I require to transfer this nitrogen from a place where we are doing fractional distillation to this heating? Don't you think I require transferring gas from the reactor in a Haber process to this cooling? Don't you think I require transferring this pulp
Yes, sir.
into a bleaching chamber, then transferring that from a bleaching chamber to a filtration chamber. Then from filtration, after I have separated out the solution, I have got the bleached thick fiber. I will need to compress that, isn't it? Don't you think I require to transfer molten glass from the place where the glass has formed, your furnace, into a mold, and then cooling I will require to transfer heat outside. Okay. So can we put this as another stream, another what shall we say, another category? I need to transfer fluids from one equipment to another, or I need to mix them. That itself is a process of transferring fluid. It's a question of, let's say I'm making a slurry of water and this wood pulp or wood fibers. I need to mix them together. In order to mix them together, I need to transfer liquid water from one part of the vessel to another part of the vessel. So if I, let's say for example, if I have a vessel like this, I fill it up with water, and I have wood pieces which I have put in. If I have to make a uniform slurry, I need to mix this water and this slurry together. So don't you think I need to transfer water from one location to another location in the vessel? So that's also a transfer of material from one equipment to another equipment, or from one part of the equipment to another part. So I will say, rather than saying from one equipment to another, transferring fluids from one location to another location. That location may be another equipment, or it could be another location in the same equipment, same vessel, same device. Can you think of some more common features?
Storage.
Excellent.
Purifying.
Purifying. Now, purifying, doesn't it come under this category? Physical process. That purifying is a step having different things. It could be crystallization, it could be distillation. Have you done crystallization anytime?
Yes.
No, sir.
Right.
Yes.
So it's a way of purifying.
Yes, sir.
Drying
Yes,
is a way of purifying. Distillation is a way of purifying. So yes, you are right, purifying, but that purification consists of several different kinds of operation. That's why we are clubbing them all into physical processes. Filtration. Filtration is separating one component from another component. Separating liquid from solid. Okay, storage. What else do you think are common features to all these processes?
Waste management.
All right. What else?
Calculations for yield.
Calculations for?
Yield, at how much we got the product.
No, that's okay. We will use calculations for calculating some things, but I'm just describing the processes right now. I'm just asking you to find out what do you think are the common features in all these processes.
Supplying electricity.
Electricity, all right. Yeah. Let me put that somewhere. Let me put that somewhere. Oh, generating electricity, maybe put it as another. Let me put it as generating and supply heat and electricity. All right.
Okay, sir.
Okay, anything else do you think is common to all
Sir,
these processes?
sir, change of phase will come in reactions or or transfer of heat.
So change of phase, is there a reaction involved when you change a phase? When you boil a water to make some tea or whatever you are making at home, what some of the water gets evaporated. Do you think a chemical reaction happens?
Not really.
No.
No,
Not
sir.
really. Not really means what? No.
No.
Do you think a reaction happens?
No, no, sir.
So vaporization. Do you think the H and O bond is breaking?
No.
Do you think this bond is breaking and then OH is vaporizing, or this whole thing is vaporizing?
Whole thing.
The whole.
Correct. So when we say reactions and reactors, some bonds are broken and new bonds are made, right?
Yes,
So
sir.
vaporization, condensation, change of phase from solid to liquid melting, or from liquid to vapor boiling, or from vapor to liquid condensing, or from liquid to solid freezing. So these are all physical processes. Okay, anything else do you think that happens?
So,
Reaction
introduction of the
conditions.
catalyst and reuse of the catalyst, like reusing the catalyst again.
Reusing the catalyst. All right. So don't you think that comes under this waste management, if you like? Well, catalyst is not a waste, but yeah, okay. Um, See, rather than calling just catalyst,
Using byproducts.
yeah. So one second. Let me just say that rather than saying just only catalyst, um, can we say? Let me put that here. Process integration.
Yes, sir.
So this may be that you
Even
recycle the
energy. Yes,
yeah,
sir.
correct,
Even
correct.
energy.
I'm just coming to that. You might recycle the catalyst, but you see here the nitrogen and hydrogen that you have supplied, you are recycling that nitrogen and hydrogen back to the process. Or as Dharmik said, you are recycling, so to say, the heat from this reactor to the step where it is required for heating of nitrogen from 77 Kelvin to 400 degrees centigrade. So shall I say recycling of catalyst, recycling of solvent, raw materials, energy from one location to another location, although we are not calling it as recycling energy, but that comes from, we are using the energy generated in one part of the process or one step of the process and using it in another step or another process. Okay, anything else?
Sir, so
So
process
reaction
integration
conditions.
means making a process eco-friendly or efficient.
So that all
Right.
that comes under waste management, and I will give another fancy name for that. I will just explain what I mean. I will give a name called as sustainability. Let me explain. I will, as we go along, we will see in our course what we mean by sustainability. Okay, what else?
So reaction conditions.
Reaction conditions are all here, right? Whether I want to do the reaction at 500 degrees centigrade, whether I want to do it at 400 atmospheres, whether I want to do it at 350 degrees centigrade, the sodium silicate making between sodium hydroxide or sodium carbonate and silica or sand, we are making maybe at 1500 degrees centigrade. So all that comes here: temperature, pressure, catalyst, solvent, all that comes under this category. Okay, any other common thing that you see?
Selectivity of product.
All that comes here, right? I am choosing a particular temperature, I am choosing a particular pressure, I am choosing a particular catalyst, I am choosing a particular solvent, that I get my desired product to the maximum extent.
Okay, sir.
Anything else do you think it comes?
So raw materials and their
Yes, sir. Raw materials.
The raw material is a common thing, but I'm talking about the process now. What are the different steps involved in processes? So all that raw material, waste, outputs, byproducts, all that has come here. We are talking about different things that are required in the process to make that process possible.
So analysis of monitoring of a chemical reaction.
Say that again.
The analysis or monitoring of a chemical reaction.
Monitoring. Thank you. Who was that? What was your name? Rishabh, you
Sir
said that?
Rishabh Chauhan. Yes,
Okay.
sir.
Monitoring. Monitoring means, what does it involve? What do you think monitoring involves?
The analysis of the reaction and its
Analysis
conditions, that
whether
is
your product form
proper.
is proper or not properly formed, what is the selectivity, how much product has formed, how much byproduct has formed. But
Yes, sir.
don't you think that if I choose a catalyst properly, if I choose temperature, if I choose pressure properly, don't you think I require to actually monitor process conditions? How much catalyst is going, how much solvent is going, how much temperature is there in the reactor, how much pressure is there in the reactor. If I monitor pressure, temperature, catalyst, solvent, all those things, if I monitor, there is no really reason why I need to monitor my product. Yes, I will of course monitor how much product has formed, but I am going to use another word for monitoring, or a slightly more involved aspect. Can we say controlling the process conditions? Which means, suppose I want the sodium silicate reaction, I want to form sodium silicate at 1500 degrees centigrade. I will not allow temperature to rise beyond 1500 degrees centigrade. I will not allow temperature to fall below 1500 degrees centigrade. If I want to make fractional distillation of air to make nitrogen, I will not allow temperature to fall below what is required, maybe 77 Kelvin, 100 degrees Kelvin, whatever temperature is required. So don't you think the common feature in all these processes is controlling process conditions, so that we get our product properly? And rather than using the word properly, I will say I will make the process or the product economically attractive. If I don't control temperature, maybe along with sodium silicate, some other byproducts will form which will not make the glass have a nice texture. Or if I don't control the temperature and pressure in Haber process, I will not form ammonia to that particular extent. I will have to keep on recycling more, isn't it? Or I may get another byproduct, may not be in ammonia, but in some other process I may get another byproduct at, let's say, if I want to maintain temperature at 100 degrees centigrade, if I don't maintain temperature, maybe temperature rises to 120 degrees centigrade, I will have some other byproduct formation. Especially if you are making nitrated products, drugs, many drugs, they are nitro compounds. So if you don't control the temperature, there may be an explosion in the reactor, because the product is thermally sensitive. So rather than saying monitoring, Rishabh, can I say controlling process conditions?
Yes, sir.
Okay.
Sir, packing.
Packing, all right.
Sir, safety of the condition, safety of the people who are doing the process.
Safety. Storage, packing, okay, bringing in raw materials, how they are brought in tankers, how they are shipped, how the product is shipped, stored in drums and packed in drums and shipped, stored. Anything else?
So management cost.
Say that again, Amrapali. Say that again.
Yes, so the cost of the reaction, the feasibility.
Ah, very nice. Are you making all these processes for charity, or are you making these processes for making a profit? The economic aspects have to be looked at. Means, what is the price of raw materials, what is the price of byproducts, what is the price of solvent, what is the price of catalyst, at what price can I sell my product, isn't it? So economics is very important. What else?
Disaster management.
Well, you have to do the management so that disasters don't happen. Isn't that a better way of saying, than rather than allowing disaster to happen and managing the disaster?
Yes, sir.
Safety, sustainability,
Sir,
waste
sir,
management.
application of the product.
Application is that the common thing, or application is my quality of the product is decided by what application I want, isn't it? What I make, I am making a product. I am making a product. The quality of that product, I am making a paper as a product. Quality of the product that I want a paper for let's say making notebooks, or I want a paper for packaging, or I want a paper on which printing will be done. Don't you think the quality of that paper will be different? Or I want to have a paper for making newspaper. Don't you think the quality of that paper will be different?
Yes, sir.
Don't you think the process that we are using to make the paper, don't you think the process conditions will have to change if I want to make paper for printing, or if I want to make paper for newspaper, or if I want to make paper for making notebooks, or if I want to have a paper for packaging?
So raw materials would change, right? The process would be similar.
Similar, but conditions, would they be same, identical? Don't you think that I will take different kinds of wood for different kinds of paper?
No, sir.
No, we will have different. Or let's say I want 99% ammonia, pure ammonia, or I will want 99.99% pure ammonia. Do you think the process will be different? Or say, for example, if I have oxygen as a byproduct, suppose I want oxygen 93% pure medical grade, or I want oxygen which is 99% pure for using in steel plants. Do you think the raw materials will be different, or do you think the conditions and hardware will be different?
The conditions and hardware will be different.
Conditions and hardware will be different, right? So that is all come here. So product quality is all come in internally into all this. We are controlling conditions, temperature, pressure, so that we can get a economically attractive. That is one. Now that we have said economics as another category, we get a product of a desired quality. Okay, anything else?
So machinery for carrying out the reactions.
Right, so all those things are here. Reactions and reactors, equipment, hardware is all here. What hardware do I require for doing all these things? It's already there. Anything else? Can I tell you a secret? Do you know the secret that I'm going to tell you?
No, sir.
No. Can you guess?
Sir.
Can you guess the secret? No? No guesses? Here is a secret. This is all that chemical engineering is. This is all that you're going to do in all the 4 years and rest of your life. Let me give you an example. Let me give you an example. The reactions and reactors that you are going to talk about, they are all going to be part of a course called as Chemical Reaction Engineering, semester 5, and multi-phase reactors, semester 6. The physical processes that we talked about, they are all going to be part of the course called as Unit Operations, semester 4, Chemical Engineering or Separation Processes. I think Unit Operations is now called as Chemical Engineering Operations, and Separation Processes, semester 5. Transferring heat, generating electricity, generating heat, they are a part of courses called as Energy Engineering, semester 4. Heat transfer, semester 5. Transferring fluids from one location to another location is going to be a part of course called as Momentum and Mass Transfer, semester 3. Storage, packing, right? Bringing in something called as project engineering or process engineering. There is a course called as project engineering and economics in semester 7, right? So the economics part that is here, that is all going to come in this project engineering and economics course. Controlling process condition, there is a course called as process control, semester 6. Waste management, safety, sustainability, there is a course called as environmental engineering and process safety, semester 6, right? Each of the things that we have talked about today, integration, process integration, there is a course called as process development, and engineering, semester 7. Each of the things that we have talked about today is a separate course in one of the 4 years that you are going to study. Besides that, you need to study physics and chemistry and maths and biology because of The process may be a physical process, chemical process, biological process. The rate of that process is going to be decided by chemistry, physics, biology, if you're making pharmaceutical compounds. So there are courses on chemistry, there are courses on physics, there are courses on biology, because there may be biological processes that are used to make drugs. So we need to study biology as well. So all these basic sciences courses that are there. We need to, in order to all these things quantitatively, you need the maths courses, because you need to write equations, you need to solve them, you need to predict what is going to happen. Right? You need the general engineering courses like civil, mechanical, electrical, instrumentation, so electronics. All those basic engineering courses are required, because they are going to govern all these various steps that are there, various categories that we made. Right? You need engineering graphics. There is a course on equipment design and drawing, 2 courses. Because finally, whatever we design, whatever hardware, somebody was saying hardware, right? Whatever hardware we require for doing all these things, for doing all these operations, somebody has to fabricate that hardware, right? Somebody has to install that hardware. We need electricity, we need power to operate that hardware. So these general engineering courses are there. Equipment design kind of courses are there, that you design that equipment, you draw that equipment, so that the drawing will go to fabricator, and then the fabricator will make the equipment. Once that fabricator makes the equipment, then it will come to your plant. You will have to install that equipment. So civil engineering is required, mechanical engineering is required, electrical engineering is required, electronics is required, right? So all the courses that you are going to study, whether they are from chemical engineering department or whether they are from other departments, all of them are required, because we require them for doing different things which are common to different processes. And that's the beauty of chemical engineering, because the process that we may be talking about could be chemical, could be physical, could be biological, could be inside the body, could be delivering a drug to the body, could be delivering a drug to kill a particular virus that is creating all kinds of issues these days. So you might be having a process, your product might not be a compound, your product may be delivering a drug to kill a virus in a body part. So you will have a drug, you will have other things, formulation kind of things. You will make the formulation. That formulation will be delivered into the body. Then the drug will be taken up. Then the virus would be killed. Right? And you have metabolism of the drug. Right? So your process can be killing a virus in the body, right? But that process you can analyze based on all your principles of generating and transferring fluids from one location to another location. So here drug is something that you have to transfer from your blood to the cell where that virus is hiding. You have to make sure that the virus is killed. There is a certain amount of concentration of the drug that is required. There is a certain process, certain rate at which the virus is killed. There is a certain rate at which virus duplicates. You have to ensure that the rate of killing is more than the rate of duplication of the virus. Right? Physical processes, metabolism, dissolution of the drug. You take a tablet, that tablet goes in the stomach, it dissolves, it is absorbed in the blood, it is transferred to a process where, to a place where the virus is affecting. Waste management. What happens to the drug? Does it cause side effects in the body, or is it discarded from the body safely? How do I control? How do I control the rate at which drug is delivered? If the rate at which drug is delivered is too small, patient will not recover. If the rate at which drug is delivered is very high, patient will have side effects. So controlling the rate at which drug is delivered, controlling the place at which drug is delivered. Okay. You think about any process, you think about any aspect, you can break them down into these several categories, and that's why chemical engineering is such a versatile profession, that you can apply it to different situations, not just making plants and making chemicals all the time. It can be very, very different things. Have you interacted with any of your BTech friends? I think hardly any chance for that, for any interaction. At least during admission, you would have seen, no, there are different BTech branches.
Yes, sir.
Yes, sir.
So there is a foods branch, there is a pharmaceutical technology branch, there is a plastic and surface coating branch, there is a textiles branch, there is a oils, oleochemicals branch, there is a dyes branch. All these different branches that are there, no, they are all going to talk about their specific products. But we as chemical engineers can look at any of these products from a unified perspective. So whether it is making a dye, or making a paint, or making a particular textile or a fiber, we can look at it in a generalized manner and try to describe the process or try to quantify the process into the different categories that we have listed as verticals. Okay. So which chemical we are talking about, or which process we are talking about, whether it is delivery of a drug, whether it is making of polyethylene, a plastic, or whether it is making some dye, it does not matter, because the principles are the same. And all these 4 years, that's what you are going to learn. All these very basic principles. Okay. And all of them, finally, you are going to get to use them in your 4th year in a topic or a subject called as home paper, where you will have to combine all these operations and processes and reactions and safety and all those things you will have to use in your final year project called as home paper. So the point that I am trying to make are these. So we have general principles which we are going to study in the coming 4 years, they are applicable universally. Okay. Second thing that I want to emphasize is all the courses that you are going to study are required. It is not that we forget, we study physics last semester, we studied math semester, now we can afford to forget about it. Now that result is over, result is out, now that we can afford to forget about what we learned in the last semester. That's not the case. You are going to need something that you are going to study in your semester 3, momentum and mass transfer, or semester 4, Cheminge operations. You are going to require it in, say, process control. You are going to require it in process safety. You are going to require it in process development. You are going to require it in project engineering and economics. Okay. All these courses are required and they are dependent on each other. Okay. So don't take any course lightly. Don't take any course and say, that is not going to be required. Everything is going to be required at some point of time. And it is for your second year, your syllabus is what you are studying in second year plus what you have studied in first year. In your third year, the syllabus is what you have studied in your first year and what you have studied in your second year and what you have studied in your third year. In the fourth year, the syllabus is not just fourth year syllabus. It is first year syllabus plus second year syllabus plus third year syllabus plus the fourth year syllabus. Right. So syllabus is cumulative. You can't say, we were taught this in semester 3 and therefore I don't remember it in semester 7. That's not acceptable, because you are taught in semester 3 and it is required in semester 7. So momentum and mass transfer is required when you start doing reactions in semester 5 and 6. It is required when you start doing separation processes in semester 5. Right? So you can't say that I've forgotten because it is in semester 3. No longer the case. Okay. Don't get scared. Okay, I'm not trying to scare you. I'm just telling you that all the things that we are going to talk in this course, we will talk about everything. Okay, we'll talk about everything very briefly. So by the end of this course, the silver lining, at the end of this course, you are going to be 80% chemical engineers.
So let's begin.
Unless what? You want to say something, Atharva?
No, sorry, my mistake.
No issue. You can talk. So you are going to be 80% chemical engineers. All the basic concepts we are going to study in this course. And later on, you just more and more applications and more, of course, into details of that course. Okay, more and more details of that concept. Okay. So we are going to have a lot of fun. We are going to talk about different things. We are going to have fun only if you keep on interacting like you did today. It will not be a one-way course. Okay. Want a break of 5 minutes? We'll have a break of 5 minutes, then we can continue for another 15-20 minutes. Is that okay?
Yes, sir.
Yes, sir.
Yes, sir.
Break of 5 minutes. It is. We will meet at let's say 10 minutes past 10. 7 or 8 minute break. Okay, shall we start again?
Yes, sir.
Yeah. So this is what we are going to do in this course and in the coming subsequent coming 3 years. What we are going to start with is something that may seem very easy for most of you, but that's good. We are going to start with some easy concepts first. In all these cases, whatever you are going to do, right, you are going to have to communicate with other people different things. You might have to communicate temperature, you might have to communicate pressure, you might have to communicate concentration, you might have to communicate the rate at which something is coming in, something is going out. So first thing that we are going to talk about is what are the units of different quantities and how do we convert units from one set of units to another set of units. That's what we are going to do first. So any particular quantity that you want, and we can talk about that quantity and what are the different set of units in which we express that quantity and how do we convert one set of units into another set of units. So somebody has a preference, which quantity should we talk about first?
Mass.
Gas mass. Polarity.
Say that again.
Mass.
Polarity.
Mass. Okay, mass, right. So mass SI unit is of course kilograms, but we talk about grams, we talk about tons, we talk about pounds. Any other unit that you are aware of for talking about mass? No? No?
Quinton.
Quintal, okay. Quintal, all right.
Stone.
Stone, right. Very nice. Who was that? What was your name?
Also Amrapali.
Amrapali, all right. Okay. Right, so just one thing before we start converting units from one set of units to another set of units. Look at this. Oops, I should not circle this gram. Do you see what I have circled in red? What does it tell
Yes,
you?
sir. It is a prefix.
Prefix. All right. So for example, if I'm talking about meter as a unit, okay, centimeter is a centi is a prefix, decimeter is a prefix, millimeter, milli is a prefix, okay, or let's not worry about other things. Kilometer is a kilo is a prefix, and if you want to go even lower, millimeter, okay, then we go 3 steps lower, then we talk about micrometer, then we still go 3 steps lower, we call as nanometer, okay. So prefixes that we are using tells us multiples of what that quantity is. So if I say meter, a millimeter is 1,000th of a meter. Micrometer, so millimeter is 10 raised to minus 3, micrometer is 10 raised to minus 6, nanometer is 10 raised to minus 9, kilometer is 10 raised to 3. Okay, and below nano also we have something.
Angstrom, picometer,
Angstrom.
Fermimeter.
Right. Picometer.
Fermimeter.
femtometer.
Right. So 10 raised to minus 12 picometer. That's more than enough. Okay, 10 raised to minus 15, 10 raised to minus 18. Let's not go into that. Right. So along with the quantity, along with the unit, we also sometimes use this prefix when we want to talk about 10 raised to 3, 10 raised to 6, 10 raised to 9, 10 raised to 12, or 10 raised to minus 3, 10 raised to minus 6, 10 raised to minus 9, 10 raised to minus 12. Okay, so how do you convert one from the other, right? So ton, so 1 ton, 1000 kgs, 1 pound, 0.454 kgs, okay, 1 quintal, 100 kgs, right? It's very easy, very straightforward. Any other quantity that we want to talk about? Length?
Temperature.
Right, so length we use meters, centimeters, all those things that we have talked about. Okay, feet, yards.
So,
Yeah.
so what is the conversion for stone?
Say that your voice is breaking. Voice is not clear. What are
So
you saying?
for stone, sir.
First,
Stone.
first stone. So 1 stone. How much is 1 stone? Who suggested stone? Somebody suggested redstone.
Yes, sir. I've
Amrapali,
heard.
yeah, 1 stone is
6.35.
So 6.35 kgs.
6.35 kgs, and in terms of pounds,
Around 13 or 14 pounds.
14 pounds. Right? 14 pounds is 1 stone. So that's why the unit conversion to kgs is something weird. But yeah, 1 stone is 14 pounds. Right. Temperature, somebody was saying. Temperature, yes. So temperature we measure in degrees centigrade, degrees Fahrenheit, Kelvin, Rankine. Any other unit?
Sir, for mass, we can even use ounce.
Ounce, yes. Right. Okay. What is the next quantity that you would like to take? Length we have got, mass we have got, temperature we have got, time, basic quantities. Let's talk about time: seconds, minutes, hours, days,
Light year.
week, light year.
Light year would be unit of length.
The light year is a unit of distance.
Thank you very much. Yes, absolutely. Light year is a unit of distance. It is the distance that the light travels, or somebody traveling with the speed of light would travel in 1 year. So light year is a unit of length, not time. Thank you. Right.
Sir, what is that conversion factor between R0 in temperature and in Kelvin?
Kelvin and Rankine, if you see some old books, some 463 something, I mean, I also don't remember now very often, because not something that you use very often, that you if you use old textbooks, you will see the unit of Rankine used, especially when people started talking about engines and all that. 460 something, 460 Fahrenheit or something like that. I'm not too sure. I will have to look at it, but yes, but we are not going to use it ever in our life. I just wanted to mention so that you have heard it sometime. But yeah, I mean, let's not worry too much about Rankine. Okay, next quantity that you would like to talk about?
Pressure. Energy.
Yeah, okay. Before we talk about pressure, we will talk about some other quantities.
Amount of substance.
Amount of substance is mass, right?
Moles.
Moles. Okay.
Number of
moles. So moles is, we talk about gram moles. So for example, if you are talking about moles, if I have let's say 18 grams of water, that's equivalent to 1 mole of water, right? Isn't it?
Yes, sir.
But because we are using grams, we should be saying 1 gram mole of water. If I, let's say, have 18 kilograms of water, I can say it is 1 mole, but that mole is now kilomole of water. That's same as 1000 gram moles of water. Right? And sometimes what we do is we don't write this gram. We don't write this gram. We just say mole. But when I say mole, it is understood at it is gram moles. All right. So if you are having, let's say 18 kilograms of water. So if you are saying, let's say you are having 18 pounds of water, we would call that as 1 pound mole. If you are having 18 stones of water, we could call it as 1 stone mole. All right. Is that okay? So just like we are having grams and kilograms, if we have, let's say 18, not grams, but 18 milligrams of water, what would we call, what we would convert that into moles? What would we get? What would we get?
1 millimole.
Or minus 3 mole of water.
Right, 10 raised to minus 3 mole, or we can call it as 1 millimole of water. If we are having 18 micrograms of water, we would call it as 10 raised to minus 6, 18 into 10 raised to minus 6 grams of water. So this is same as 18 into 10 raised to minus 6 grams of water. This is same as 18 into 10 raised to minus 6 gram moles of water, which we can say is simply 18 micromoles of water. Is that okay?
So it would be
Sir, micromoles of water, not 1 micromole.
Oh, sorry.
So it will be 1 micromole of water.
Yeah. Sorry. One.
and so also 1 gram mole.
Yeah, pardon?
So gram mole also it would be 1 only.
Gram mole, it would be 1, so I've written 1 only.
No, sir, 18 into 10 raised to minus 6.
Oh, sorry. 1 into 10 raised to minus 6. All right. Thank you. Just proves that you are awake. Very nice. Okay, next quantity.
Current.
Okay. Amperes and microamperes and milliamperes and kiloamperes. Volume. Okay. So volume, we would use meter cube would be the SI unit, but I could have centimeter cube, I could have millimeter cube, I could have kilometer cube, I could have decimeter cube. By the way, decimeter cube, any
Liter.
Right?
Liter.
That is same as liters. We could have gallons. You could have a UK gallon. You could have a US gallon. So UK gallon. Metric.
Metric ton. What is that mass?
ton is a unit of mass, right? Metric ton, right? So metric ton just means 1000 kgs, because there used to be, so all these problems are created by this one tiny country that is there in Europe, that sort of ruled many countries in the 18th and 19th century. They had this weird notation that whatever they say, everything will be standardized, and of course that did not materialize. So they used to call it as a short ton. So why they used to, the short word came later, but they used to call it as ton. That was something like 2000 pounds. So it became a short ton because it is not exactly 1000 kilograms. So then people had to introduce metric ton. Right? It's the country that is using the word pounds. Of course, you know what country I'm talking about. Okay. So US gallons, UK gallons, barrels. Crude oil is measured in terms of so many million barrels per day of oil production. Barrels is like 158, 159 liters. UK gallons 4.4 liters, US gallon 3.8 liters, 3.78 something liters, right? So you see the use of prefixes in such cases as well, right? Okay, next quantity.
Energy.
Before we go to energy,
Force.
force. Okay, good. Force. SI unit?
Newton.
Newton. Okay, any other
Dyne.
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 One dyne
kg
is,
force.
1 Newton is, we'll talk about that. Very nice, very nice. Very nice. So forget dyne, 10 raised to 5, but 10 raised to 5 dynes is 1 Newton. Forget about that. Kg force, right? Or we could have a pound force, right? What this tells you, it consists of two words, kgs and F. So what it is a force that would be exerted by 1 kg mass, isn't it? So 1 kilogram force would be the force exerted by 1 kilogram. The force exerted would be 1 into 9.81, that is G. So this would be 9.81 newtons, kilogram meter per second square, acceleration due to gravity. So that unit is Newton. So kilogram meter per second square is nothing but the unit that we call as Newton. So when I say 1 pound force, there are two things in that, force and pound. So 1 pound force would be force exerted by 1 pound mass. That means the force exerted by 0.454 kilogram of mass, isn't it? So let's try to convert, let's say 1 kilogram force. I want you to tell me how many pound force is that. How will we get that?
So by multiplying by 0.454 into 9.81.
Do I have to multiply by 0.454 or divide by 0.454?
Divide.
Right. So if I want 1 kg force, what do I want? I don't want this kg there. I want pound there. Right. So if I take this 1 kg force, 1 kg force, if I multiply by a quantity that will have units of pounds and it will have in the numerator units of kg in the denominator, then this kg would cancel out, cancelling of units, and then I would have pound and force. So if I take 1 pound, that's 0.454 kgs. Okay. So 1 kg force would be 1 divided by 0.454 pound force. Do you agree?
Yes, sir.
So who was saying multiply by? Is that clear now?
Yes, sir. It's clear now.
Okay. Okay. So we will continue talking about different quantities and converting one set of units into another set of units. That will be clear to you as we go along. It's time to stop here for the day because you have another class at 10:40, so you can have a 5 minutes break as well. So we'll stop here for the day. I will share the recording through the Google Classroom. Any other quick question, any other quick doubt that you have?
So kg force, would it vary from planet to planet if we go to sea?
Yes, yes, absolutely. Because the G would vary from planet to planet. All right. So the days of colonizing Mars have not yet come, so we don't have to worry about it. So we will just say 1 kgf is 9.81 newtons for now. Is that okay?
Yes, sir.
So shall we stop here for the day? So next class, we need to have calculators. Everybody should have a calculator because we are going to start calculating. This was the only lecture where I talk so much and you people listen. Henceforth, I will talk very little and you people will solve and tell me the answers for the rest of the course. All right. I just have to talk and describe the problem to you. Then you solve and then you talk. Okay. I will stop recording. So calculator is a must from next class.